complement of a set. So let's begin our discussion on the complement of a set. As we delve deeper into set theory, which, as you know, is all about collections of objects, understanding the idea of a complement becomes really important. Think of it this way: sometimes we want to know not just what is in a set, but also what isn't in that set relative to a bigger group. That's where the complement comes in. The complement of a set essentially pinpoints all those elements that are not found within a particular set, but importantly, do belong to a larger set that contains everything we're considering. We call this larger set the universal set. So, the universal set is like the overall scope of everything we're talking about. And the complement tells us everything outside of a specific set, but still within that overall scope. Over the course of this tutorial, we're going to break down exactly what the complement of a set is and, more importantly, how to figure it out. We'll work through examples and use diagrams to make sure you have a solid grasp of this concept. In the following slides, we'll first define what exactly this universal set is before we can even begin to talk about complements. So, let's move on to that now. Defining the universal set. So we've just started talking about complements of sets, and now we need to lay some groundwork. This slide introduces a very important concept: the universal set. Before we can even begin to figure out what's not in a set, which is what a complement is all about, we need to know what our overall boundaries are. That's where the universal set comes in. Think of it this way: imagine you're drawing circles on a piece of paper. The universal set is like the entire piece of paper itself. Everything else, all the circles we draw, exist within that paper. Formally, the universal set is denoted by the capital letter U. I'll say that as capital U. It's the set that contains absolutely all possible elements we're considering in a specific problem or context. It's the universe, and that's why we call it the universal set, from which all other sets are created or drawn. Let's look at some examples to make this clearer. First, if we're talking about the set of even numbers, what could our universal set be? Well, it could be all integers, that is, all whole numbers, both positive and negative, including 0. So, the universal set would include numbers like -2, 0, 2, 4, and so on. Next, imagine we're discussing students in a class. In this case, the universal set would simply be all students enrolled in that class. It's everyone who's part of the group we're focusing on. Finally, let's consider something a little different. If we're looking at the letters in the word mathematics, the universal set would be the set containing each unique letter in that word. So it would be M, T, H, E, I, C, and S. Notice we only list each letter once, even though some appear multiple times in the word. Understanding the universal set is absolutely crucial because, as we'll see in the next slides, the complement of a set is always defined in relation to this universal set. So, make sure you have a good grasp of this concept before we move on. Defining the complement. So now that we've established what the universal set is, remember, that's our overall collection of everything we're considering. We can finally define the complement of a set. This slide formally defines what we mean by the complement. If we have a set, let's call it A, the complement of A, which we write as a prime, and you'll also sometimes see it written as A to the power of C, or A with a bar over it, represents all the elements that are present in our universal set, U, but are not present in set A. Think of it as everything outside of set A, but still within our defined universe, U. Now let's look at the mathematical expression. We write it as a prime equals the set of all x such that x is an element of U and x is not an element of A. Let's break that down. The symbol means is an element of, and means is not an element of. So, what this equation is saying is that a prime, the complement of it, consists of all x values, where x belongs to the universal set U, and x does not belong to set A. This might seem a bit abstract right now, but we'll solidify it with examples on the next slide. Remember, understanding this definition is key because it's the foundation for many other concepts in set theory, and as we'll see later, it has applications in areas like probability and computer science. We'll also visualize this with Venn diagrams shortly, which will make it even clearer. Finding the complement, step by step. So now that we've defined what the complement of a set is, remember, it's everything in our universal set that isn't in the set we're looking at. Let's work through a couple of examples to really solidify this concept. As we move through these examples, keep in mind that we'll soon be visualizing these with Venn diagrams, which will make things even clearer. First, let's look at example 1. We're going to define our universal set, which we denote with a capital U, as the set containing the numbers 1 through 10. So, U equals the set containing 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we'll define set A as the set containing the even numbers between 1 and 10, 2, 4, 6, and 8. Now, to find the complement of A, which we write as a prime, we need to find all the elements that are in U, but not in A. Let's break this down step by step. Step 1, we simply list out all the elements of our universal set, U as we already stated. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Step 2, next, we list the elements of set A, that's 2, 4, 6, and 8. Step 3, now comes the crucial part. We identify which elements are in U but not in A. Looking at our lists, we can see those are 1, 3, 5, 7, 9, and 10. Step 4, therefore, the complement of a prime is the set containing 1, 3, 5, 7, 9, and 10. So, we've successfully found all the elements in the universal set that are not present in set A. Let's move on to example 2 to reinforce this. This time, our universal set, U, is a bit different. It's the set of vowels in the English alphabet, A, E, I, O, and U, and let's define set A as the set containing just the vowels A and I. Again, we'll follow the same steps. Step 1, list the elements of the universal set, U, that's A, E, I, O, and U. Step 2, list the elements of set A, that's A and I. Step 3, identify the elements in U that are not in A. Looking at our lists, we see those are E, O, and U. Step 4, therefore, the complement of a prime is the set containing E, O, and U. So, with both of these examples, we've practiced identifying the complement of a set by systematically finding the elements in the universal set that aren't in the set we're interested in. Remember, defining that universal set is key, and we'll see how this all comes together visually on the next slide when we use Venn diagrams. Visualizing with Venn diagrams. So now let's move on to visualizing this concept of a complement using Venn diagrams. As we've discussed, finding the complement can sometimes feel a little abstract, so a visual aid can be really helpful. Venn diagrams are a fantastic way to represent sets and their relationships. Remember, the universal set, we denote it as U, is everything we're considering in a given problem. In a Venn diagram, we represent this universal set with a rectangle. Think of the rectangle as the boundary of everything that's possible within our current context. Now, any specific set, let's say set A, is represented by a circle inside that rectangle. The circle contains all the elements that belong to set A, and here, S where the complement comes in visually. The complement of set A, which we've been denoting as a prime, or sometimes A with a bar over it, is simply the part of the rectangle that is outside the circle representing A. It's everything in the universal set that is not in set A. So, if you were to shade the area outside the circle, that shaded area would visually represent a prime. The complement of A. This makes it much easier to grasp what the complement actually is, all the elements in the universe that aren't in our set. This visualization will be particularly useful as we move forward and start applying these concepts to more complex problems, like those involving probability, which we'll touch on in the next section. It's a great way to check your work and make sure you're correctly identifying the elements that belong in the complement. Significance of complements. So now that we understand what the complement of a set is and how to find it, let's talk about why it's important. This slide highlights the significance of complements. They aren't just a theoretical concept within set theory, but actually have practical uses in many different areas. Let's look at some specific applications. First, in probability, the complement of an event is incredibly useful. Think about it this way. If you're calculating the probability of something happening, the complement represents the probability of that thing not happening. So, if you want to know the chance of rolling a 6 on a die, the complement would be the probability of not rolling a 6, meaning rolling a 1, 2, 3, 4, or 5. Together, the probability of an event and the probability of its complement always add up to 1, or 100%, representing all possible outcomes. Next, we have logic. Here, the idea of a complement directly relates to the concept of negation. In logic, to negate a statement means to say that it is not true. Just like the complement of a set contains everything not in the original set, the negation of a statement expresses everything that isn't covered by the original statement. Finally, consider computer science. Complements are used extensively in areas like database queries and data manipulation. For example, when you're searching a database, you might ask for everything except certain items. This except operation is essentially finding the complement of the set of items you don't want. They're also used in Boolean algebra, which is the foundation of digital circuits and computer programming. Complements are fundamental in set theory, meaning they form a core building block for more advanced ideas. But their usefulness extends far beyond just mathematics itself. So, as you can see, understanding complements isn't just about mastering a set theory concept. It's about building a foundation for understanding ideas in probability, logic, and computer science. In the next slide, we'll quickly cover some common mistakes students make when working with complements, so we can make sure you avoid those pitfalls. Common mistakes. So, the first common mistake we see students make is forgetting to define the universal set. Now, remember from earlier, the universal set, we called it U, is absolutely fundamental. It's everything we're considering in a given problem. Without a clearly defined universal set, it's simply impossible to accurately determine the complement of a set. Think of it like this. If you don't know the boundaries of your universe, how can you identify what's outside a particular set within it? It's like trying to find things that aren't in a room without knowing where the room even is. And that leads us to the second common mistake. Sometimes, students accidentally include elements in the complement that aren't actually part of the universal set. Remember, the complement contains only those elements that are in the universal set, U, but not in the set A. So, always double-check that every single element you've included in your complement is also present in your original universal set. If it's not in U, it doesn't belong in a prime or the complement of A. Let's move on to a really important part of understanding complements, recognizing common mistakes. This slide will help you avoid some pitfalls as you practice. We'll be wrapping things up soon, and in the next slide, we'll summarize the key takeaways from this entire tutorial so you have a solid understanding of complements and how to work with them. But keep these mistakes in mind as you practice. Avoiding them will save you a lot of frustration. Key takeaways. First point, the complement of a set, which we represent as a prime, and remember, the prime symbol just means we're talking about the complement, contains all the elements that are in our universal set, U, but not in set A. So, if we have a universe of possibilities, the complement of A is everything outside of A within that universe. Next, and this is really important, a clearly defined universal set is crucial for determining the complement. Think about it. If you don't know what your overall universe is, you can't accurately figure out what's not in a specific set. We saw this right at the beginning. Defining U is the very first step. Now, remember those diagrams we used? Venn diagrams can be used to visualize complements. The universal set is the whole rectangle, and the complement of A is simply the part of the rectangle that doesn't overlap with the circle representing A. It gives you a really clear picture of what we're talking about. Finally, complements aren't just a theoretical concept. They have important applications in various fields. We touched on this briefly, but think about probability. The complement of an event is everything that doesn't happen. It's also used in logic and even in computer science for things like database searches. Let's recap everything we've learned about the complement of a set. This is our final slide, and it's all about solidifying those key takeaways. So that's it. You should now have a solid understanding of what the complement of a set is, how to find it, and why it's useful. Remember to always define your universal set, and don't hesitate to use a Venn diagram to help you visualize the problem. Are there any questions about anything we've covered?